everyone, I hope you're all doing well. In today's video, we're going to start a new module, Module 3, which is all about chemical bonding. So we're going to jump back to Chapter 4 and go over sections 4.6 through 4.8. And then later on, probably next week, we'll go over chapters 6.1 to 6.7. So there is a study guide available on Canvas for Module 3. And really, when we're talking about chemical bonding, we're really talking about electrons. So when you think of bonding, think of electrons. All right, so we're going back to Chapter 4. So before we start talking about electrons in a little more detail, we're going to talk about electromagnetic radiation. So we experience electromagnetic radiation in different forms. So most often we experience it in the form of light. You might also occasionally see a rainbow. That's also electromagnetic radiation. Or if you've ever had an X-ray, that's also electromagnetic radiation. So electromagnetic radiation consists of energy particles that move as waves of energy. And electrons exhibit this type of behavior. So even though we think of electrons as these little subatomic particles that exist in an atom, they can actually move like a wave or have a wave-like nature. And that's why we're talking about electromagnetic radiation, because electrons behave in the same way. So when we're talking about waves, let's see, I'll draw a better wave down below. The distance between the peaks of the waves is called the wavelength. So the distance between those two peaks, that is the wavelength. Now you can also measure the height of a wave. So if you kind of divide this in half, from that halfway point to the top of a wave, or even to the bottom, that is called the amplitude or the height. Now, the waves that are above that halfway point, we call that a crest. So the highest point is the crest, the lowest point is the trough. All right, so the reason that we care about these different definitions, now high energy radiation has shorter wavelengths. So it would be something like this, where it's just super quick and the waves are really close together. And then low energy radiation has longer wavelengths. So the distance between the peaks is very long. All right. So this is our electromagnetic spectrum, and we have low energy waves on the left and high energy waves on the right. So again, there are different types of electromagnetic radiation. We have radio waves, which are lower in energy. We have microwaves, which are also low in energy. There's infrared, which is also low in energy, and then we get to visible light. Now, visible light, this rainbow section, is a really small section of the electromagnetic spectrum. But within that visible light, we have a range of energies as well. So Listed below the visible light up above is what's called the wavelength. So that's going to tell us how far apart the peaks of a wave are. So on the left-hand side, we have lower energy waves, and that gives us a reddish color. And then as we move to the right, the wavelengths are getting smaller and smaller and smaller until we get to blue light, or kind of a purplish blue light here, which has really short wavelengths. So that's really high in energy. So again, red light is low energy and blue light is high energy. All right. Then once we move past the visible light section, we get to ultraviolet light, or UV rays. And you might already know that UV rays can be harmful to our skin if we sit outside for too long, which is why we should wear sunscreen, because that protects against UV rays. So UV rays are higher in energy. Next are X-rays, which are even higher in energy. And when you get an X-ray at a doctor's office or the dentist, for instance, sometimes they'll put this like heavy sheet on top of you to protect your organs. That's because X-rays can be harmful, but it's more of a precaution because typically they're only going to snap a very brief picture of your teeth or your bones. So they only leave, or doctors and dentists only expose you to X-rays for like a fraction of a second because they don't want to harm you. But X-rays are really useful, and they're only harmful if you're exposed to them for really long amounts of time. But you know, just to be safe, they also will put a sheet on top of you to protect your organs. And then last but not least are gamma rays, and gamma rays are the most energetic form of electromagnetic radiation. And gamma rays are the type of energy that comes off of nuclear radiation. All right. So anyway, now that we kind of can see the difference between lower energy waves and higher energy waves, we're going to kind of jump back into electrons because again, remember electrons can behave as waves. All right, so let's say that we have an element. So let's say we have barium. And let's say that we excite the electrons in atoms of barium. So maybe we're applying heat, or we have a flame with barium in it. Whatever we're doing to excite the electrons, the element will emit a color of light. So for barium, it's kind of, it looks like a greenish color here. Now, that light that barium is emitting, it actually consists of multiple wavelengths of light that are all combining together to make a greenish color. So this is kind of similar to if you have ever mixed paint colors before. So maybe you mix blue and red to make purple. Now, if you could separate out those original colors again, you would find that that purple color is actually composed of blue and red. And that's kind of the same thing here. So if we were able to gain access to a prism and pass light through the prism, this prism is going to bend all of the different sections of light that are making up that green color. So what we would see is a blue color, a greenish color, an orange color, and a red color. And those are actually all mixed together to make that original green color. So now, if we were able to detect those colors on a detector, we would get something called a light spectrum. And so we would see all of these different colors of light that are making up the color of barium. So this is our atomic light spectrum. Now, each element has its own unique atomic spectrum. So, for instance, helium has sort of a pinkish color to it when you heat it up. And if we were able to separate that, the different components of light making up that pink color, we would see a totally different atomic spectrum from barium's atomic spectrum. So now what's actually happening with those lines in the atomic spectrum, those are associated with changes in energies of the electrons. So barium's electrons were getting heated up, they were gaining energy, and that change in energy was what produced those different colors of light. So in an atom, each electron has a specific energy, and this is known as its energy level. So that energy level is assigned something called a principal quantum number, and it's given the symbol N in quantum mechanics. So we're kind of talking about the beginnings of quantum mechanics here, which is a whole other class, but we'll just briefly touch on it. So the principal quantum number, or the energy level, can be anything from 1, 2, 3, etc. All right, so as we have an increase in energy of electrons, the N value increases and electrons are farther away from the nucleus. So let me draw a picture real quick, and then we'll come back to this slide. So I'm going to draw the Bohr model of the atom. So we've got our nucleus in the middle. And then we have these energy levels that electrons exist in, and those surround the nucleus. So the first energy level, we would call that N equals 1, and then we'd label the next one N equals 2, and we'd keep going depending on how many electron energy levels there are. And then we can start placing electrons around the nucleus. So maybe there's an electron in the first energy level. Now, let's say we add energy to this atom. So let's say we're heating up this atom. What happens is the electron gains that energy, and it can actually jump to a higher energy level. So maybe it jumps up to energy level 2. Now, when that electron is at a higher energy level, it's actually less stable. So eventually it wants to relax down to a more stable energy level. So when it does that, so let's say it jumps back down to relax, it actually emits something called a photon. Which is actually a packet of light. All right. So if we go back to our atomic spectrum here, barium emits kind of a greenish light, and that greenish light is actually due to multiple electrons jumping up and down around those energy levels. So we were talking about an atom that has only one electron here, but most atoms have multiple electrons. So maybe we have some more electrons hanging out, and maybe those are also jumping up and getting excited. Maybe this electron skips up to energy level 3, and then they're all relaxing down. So maybe this electron relaxes down to n equals 1. Maybe this one only relaxes down to energy level 2. There are patterns that scientists have discovered for these different relaxation events, but the energy that's emitted, again, is what we call a photon. So it gives off a different type of light. And there's a different energy for different colors of light. So if we go back to our visible light spectrum, let's say an electron emits a low amount of energy, so it kind of emits like an orange color. Another electron might emit a bunch of energy, like a really high amount of energy, and that would give more of a bluish color. So again, that all will combine to create this green light for barium, for instance. And then other atoms will have other colors based on how their electrons move around. Okay, so going back to this slide, one last point here. The energy of an electron is quantized, which means that electrons can have only specific energy values. So if we go back to our picture of the atom, you'll notice that the electrons are sitting in very specific energy levels. They're not hanging out in the middle there. So that's not how electrons work. They want to exist in very specific places around the nucleus. They're still moving around that energy level. So if we had an atom, we would see an electron kind of zipping around, or maybe even zipping around this way, but it likes to stay in a particular energy level for the most part. All right. So now if electrons have the same energy, then they are grouped in the same energy level. So we can also think about this like a bookshelf. You might have electrons in the lowest energy shelf or in the second energy shelf. And the further away from the nucleus an electron is, the more energy it has. So this has energy level 5 has the most energy, energy level 1 has the least energy. Okay. And then we kind of already talked about this, but again, when electrons absorb energy, they jump to higher energy levels. But eventually they want to go back to a more stable energy level. So that's when they will relax down. And when they do that, they emit either a low energy wave or a high energy wave, and that affects the colors that we see coming from an excited atom. So the energy that's emitted or absorbed is equal to the differences between the two energy levels. So for instance, energy level 1 and 2 are pretty far apart, but as we get further and further away from the energy or from the nucleus, those energy levels get closer and closer together. And so the differences depend on the distance between energy levels there. Okay, so now that we know about energy levels, let's talk about sublevels. So sublevels exist within energy levels. So we're kind of going deeper into these energy levels here. So each energy level consists of one or more sublevels. And the number of sublevels in an energy level is equal to the principal quantum number n of that energy level. So for instance, let's say we have an electron in energy level 1. There's only one sublevel. But if we're in energy level 2, there are two sublevels. And that pattern continues. So scientists who were working on figuring out what these sublevels were, where electrons exist around a nucleus, they identified these sublevels as S, P, D, and F. And these are not arbitrary letters. S stands for sharp. So when scientists were detecting where electrons are around a nucleus, if electrons existed in the S sublevel, they exhibited kind of a sharp signal. P stands for principal, D stands for diffuse, and F, I'm forgetting what F stands for at the moment. But anyway, those aren't random letters. They do stand for something. All right, so an S sublevel is going to be lower in energy than a P sublevel, and a P sublevel is lower in energy than D, which is lower in energy than F. So even within an energy level, electrons can have different energies, which gets a little confusing sometimes, but we'll try to make it as clear as possible. Okay, so here's a chart that I really like. This shows the energy level for an electron. So maybe it's in energy level 1 or 2 or 3, etc. And then remember the number of sublevels is equal to the energy level. So in energy level 1, we have one sublevel. In energy level 2, we have 2. And in energy level 3, we have 3, etc. So to start, let's look at energy level 1. So the only type of sublevel in this energy level is the S sublevel. So there's only one sublevel, and it's an S sublevel. All right, and then if we go to energy level 2, we have two sublevels. We have the S and the P sublevels. So we've got S and P, and we'll talk about these boxes in a second. And then as we go up, we have energy level 3, which has S, P, and D sublevels. And then energy level 4, we also add the F sublevel. All right, so you might be wondering, what if we go to energy level 5? And that's a very good question, but we'll kind of get into that later. Okay, so you'll notice that we're representing these sublevels with boxes. Each box is referring to something called an orbital. So you'll notice that the S sublevel only has one box or one orbital. And then if we look at the P sublevels, they all have 3 boxes. So those are all orbitals. And then the D sublevel has 5 boxes. So those are all the different orbitals. And then the F sublevel has 7 boxes or 7 orbitals. So what are orbitals? So orbitals are going to tell us the probable location of an electron. So orbitals are actually telling us the orientation of an electron, essentially. So, for example, let's look at the s orbitals. So, the location of an electron is described in terms of probability. And this is because electrons are kind of tricky to track down. We can pinpoint their energy level, we can pinpoint their sublevel, but beyond that, it's hard to know both the location and the speed of an electron at the same time. So electrons are constantly zipping around within their particular energy level. So it is really hard to take a snapshot of where an electron is. So off to the right, you can see something called an s orbital. And this was modeled on a computer. And basically, what the computer scientist, I'm assuming, did was they were trying to model where an electron might be if it exists in this s orbital. And what they found was that the electron was always within this sphere. So you can kind of see the spherical shape there. And we have our three axes here, x, y, and z. So this is a 3D rendering of where an electron might be. So s orbitals have a spherical shape. And this is just determined again through computer simulations. So this electron cloud represents the highest probability of finding an s electron. Now, remember that each energy level has an s orbital. So if we go back, every single energy level has an s orbital. But remember that the higher in energy we go, the further away from the nucleus the electron is. So you'll notice that as we go from 1s to 2s to 3s, the spheres are getting bigger because an electron is more likely to be further away from the nucleus. Now on to p orbitals. So remember we said that there were 3 p orbitals, and the p orbitals start in energy level 2. So p orbitals are very strange looking. They kind of look like figure eights. And if we were to draw our x, y, and z axes, we would find that the 3 different p orbitals lie along different axes. So this would be labeled our pz orbital. Let's see, and then I'll do my best here. I have a better picture coming up. This would be our py orbital. And this is our px orbital. So each orbital faces in a different direction, but they all have the same energy. So typically, if an electron is in a p orbital, we don't really know which orbital it's in, x, y, or z. We just know it's in a p orbital. But anyway, these 3 orbitals are actually all centered on a nucleus. So if this is our nucleus, we actually have those 3 orbitals all piled on top of each other. So this is the probability for where an electron is if it's in a p orbital. And this is a much better picture of what I was trying to describe. All right. So we can see the individual p orbitals, and then we see them all overlapped on top of our nucleus there. All right, and then d orbitals get even more complicated. And again, these are all generated on a computer, so I don't expect you to draw these. You might be asked to identify s, p, or d orbitals, but um, you don't have to draw them. Okay, so remember we said that there were 5d orbitals, and they all kind of look like four-leaf clovers, and they're all facing different directions, except for this last one, which is really strange. It kind of looks like a p orbital with a donut around it. I think the technical term for the donut is a toroid, but I like to just call it a donut. And then F orbitals are even stranger. They're like 8-leaf clovers, so I won't even show you that because it's beyond what we're going to do in this class. Okay, so one last thing. We just talked about all of the different orbitals that exist. And there is something called the Pauli exclusion principle that tells us that each orbital can hold a maximum of 2 electrons. Now, electrons, we know, are negatively charged, so they naturally want to repel each other. So electrons in the same orbital repel each other. So in order to exist in the same orbital, electrons have to have what's called opposite spin. So electrons, when they're moving around, they're also spinning, and they can spin clockwise or counterclockwise. So we would call that spin up or spin down. So we want a counterclockwise electron to be paired up with a clockwise electron, if that makes sense. This is also similar to magnets with north and south ends. So if you tried to put the north end of a magnet next to the north end of another magnet, they would repel each other, right? So instead, you would want to put an electron with a north end next to an electron with a south end, and then they would attract. So same idea, but we just call electron spin up and spin down. We also can represent these electrons with arrows. So if this is our orbital, this box, we would put a spin up electron and a spin down electron in that box, and that's represented by an up arrow and a down arrow. So if we go back to our chart here, what we can do is start to fill in this chart with arrows. So let's say an atom has 3 electrons. So we're just going to start from the bottom and fill in the boxes according to energy levels. And we'll do more of this in the next lecture, but I just kind of wanted to give you an idea of what's coming up. So we can start to fill in those boxes with electrons and figure out where electrons exist around a nucleus. Okay, so we said that each orbital can hold 2 electrons maximum. So each s sublevel has 1 orbital and can hold a maximum of 2 electrons. Each p sublevel has 3 orbitals and can hold a maximum of 6 electrons. Each d sublevel has 5 orbitals and can hold a maximum of 10 electrons. And then each F sublevel has 7 orbitals and can hold a maximum of 14 electrons. So let's go back to our chart and kind of write that down here. Okay, so we can see that our s orbitals can each hold 2 electrons maximum. And then our p orbitals, we have 3 of them. And if each box can have 2 electrons, that means that p orbitals can have a total of 6 electrons maximum. And then d orbitals there's 5 of them, and each one can hold a maximum of 2 electrons. So that's a total of 10 maximum electrons that d orbitals can hold. And then f orbitals, there's 7, so that can hold a maximum of 14 electrons. So we can actually start counting up how many electrons exist maximum in each energy level. So energy level 1 can only hold 2 electrons maximum. Energy level 2 can hold 2 plus 6, so that's 8 maximum electrons. Energy level 3, we have 2 plus 6 plus 10, so that's 18. And energy level 4 can hold 2 plus 6 plus 10 plus 14. So let's see, that's 18 plus 14, so that's 32. I did that right? Yeah. All right. So that's the maximum amount of electrons that each energy level can hold. All right. So let's do a quick learning check and then we'll call it a day with energy levels. So let's indicate the type and number of orbitals in each of the following energy levels or sublevels. So A, n equals 1. So that's energy level 1. How many orbitals and what type of orbitals are in energy level 1? So do we have S, P, D, F orbitals? What type of orbital? S. So remember, energy level 1 only has one sublevel, and that's the S sublevel. And S sublevels only have one orbital, so that is the S orbital. What about the 3p sublevel? So we already know the type of orbital, that's a p orbital, but how many orbitals does a p sublevel have? 3. So there are 3p orbitals in a 3p sublevel. So if you're feeling very confused right now, don't worry. Again, this is kind of an introductory quantum mechanics lesson, so it's okay if you're confused. We'll do a lot of practice problems in future videos, so don't worry if it's confusing. I've also posted some extra videos on Canvas under Modules Week 4, and those videos also show how all of these energy levels work, what orbitals are, and that could help as well, just to kind of see other people explaining it too. All right, so that's it for today, and I will see you in the next video.